the algebra book. Okay, yesterday, and I'm sorry, I should have recorded this. We looked at triangle congruence, and we said, hey, same shape, same size. That's what it means to be congruent, and we look for this mapping. And this part, 100%, I'll tell you, is what I consider the most important thing from yesterday. The fact that we have a congruent statement that goes in a particular order tells me exactly everything that I need to know about figures. Now, there are not very many times that has happened in this book, and this may be the first, but I disagree with the authors and how they approach doing this. We can certainly do rigid motions over and over and over. We just spent a whole chapter over it. Here's the deal. I think there's better ways. There is mathematically and logical ways to do this rather than working with a piece of wax paper if needed or just trying to find these rigid motions. Now, they will always exist, but I care much more about the math and logical ways of doing these than I do about the physical motion. And it's nice that we have both, but with that said, what that means from my point of view is that as far as the rigid motion and stuff goes, did we do enough of them that you understand reflections, rotations, and translations, do you think? Okay, we could keep doing them, and we could probably do them all year long. Does anybody want to do reflections and rotations and translations all year long? If it was super easy, yes is a reasonable answer, just for the record, but me neither. So with that said, we are going to finish up 4.1. I'm not going to give you an assignment on 4.1. Like, we'll talk about a couple things. We're just going to pick a few problems in here and see if we can't roughly come up with a way to make this happen. So you don't have to do any writing, but I do need you paying attention to stuff. Okay, as I look at these two figures, my only question is, do you think that these are congruent? And how did you come to that conclusion? But this one has a pointy up, and this one has the pointy down. Okay, so we can all see that that's true, right? Now, if I said what rigid motion takes me there, can you guys tell me? You reflect over what? Over this line to flip it upside down, and then you move it right and down. Okay, there's a bunch of them. Now, we can check it. We could reflect and rotate. There's a bunch of different answers. Do we all agree that they're congruent? Now, we can't say that with certainty until we actually find the mapping. When I look at this, I think, here's my thought process. This one goes from 9 to 1. It's 8 tall. Okay, and then, so 8 tall. This one goes from 9 to 1. It's 8 tall. It's the same height. Cool. And then I realize that this goes up 3 over 2. This goes 3, 2. So those match up. And I'm looking at all the pieces, but I agree that they're congruent. I don't know that the best way to show these are congruent is by only having the option of saying, yeah, let's look. It's a reflection about this line. There's value to that, but we just did a whole chapter of it. Okay, I agree they're congruent. What about these? Without the writing, just the arrows themselves. Do you think those are congruent? If I had a rigid motion or a composition of them, how would you go from one to the other? You could reflect twice, right? Reflect over the line right between them, and then it's the wrong way, and then reflect right over the middle, and it flips up. I am certain, I have a big hangnail, sorry. I'm always really self-conscious about my hands on the screen, and I don't know why. But I bet if we pin it right here, we could probably rotate around and get it to land on itself as well with some amount of rotation. There's a bunch of ways to do it. They look congruent. We're probably just going to say they're congruent, realizing that's not truly mathematical. Okay. That's all I want to say about this section, if that's okay with you guys. Cool. I'm not going to make you do a bunch more rigid motions. We just did a bunch of them. Let's move on to some little bit mathier of a feel. All right. So with that said, let's jump in to our next section. So I'm going to clear this, and we're going to kill it. Boom. And we're going to jump in today, and we're going to look at Chapter 4, Section 2. And we're going to look in this section, 4.2, and this is going to be a weird name. It's not exactly what the name is in your textbook, but we're going to say some specific triangles. And we could probably call every section this, but there's a couple specific types of triangles that I'm going to make sure that we understand and that we get to work with because they're nice. Now, right off the bat, if I said, what are the different types of triangles? There's a few options. Can you guys sketch a triangle and then draw a different type of triangle? Okay, so let's try to list out some of them. We're going to just see if we can stumble upon the words that I want to talk about here. Give me a type of triangle. What is an isosceles triangle?
All different sizes of lines.
Okay, so this, I'm going to draw these pictures and you just tell me. So you said all different sizes. Is this an isosceles triangle? So here's a part of it. If your definition of isosceles was correct, I would agree with you. This is not isosceles, though. Have we seen another word that had iso in it?
Isometry.
And isometry meant the same, right? So something has to be the same on this. This triangle, just so you guys know, there's a few different ways we could classify it. If I make the claim that this is an obtuse triangle, and I'll write down the stuff that we need, just so you know. Is that an obtuse triangle, and what does that even mean?
Yes.
Okay, what does it mean? There is an angle bigger than 90 degrees, right? This is a big angle, and we just happen to use the word obtuse rather than a big angle. So it is an obtuse triangle. That's one way we classify it. All three sides are different lengths. This is not our isosceles. You don't have to write this one down, but just since it showed up, it's a scalene triangle. Scalene is a word for all different sizes. Okay, what's an isosceles then?
Two the same, one's different.
Two the same, one's different. And we'll clean that up, but this triangle is also a triangle, but it's a different type, right? This one, that's true. This is our isosceles. Okay, this is one of the two that we'll be talking about today. I'll help us refine this. Any other types of triangles that you guys have? A right triangle. Is that a right triangle? Now, for sure. That's a right triangle. I'm cool with that. Could you make a right isosceles triangle?
Yes.
If those are the same, now it's isosceles and it's right. Okay? Any other types? An acute triangle. I'm not trying to make them like small necessarily for any particular reason. We'll do it there. Now we'll do it there. Nope, still doesn't work. Why am I struggling with this? Here we go. Why is this an acute triangle? All the angles are acute and small, right? Like that's the silly way to remember it. They're all less than 90. Any other special name that this particular triangle might have? If it's perfect, and that's like, I get what you're getting at there. Would you believe it if I put these marks on there? So not only is it acute, what else could you tell me about it? All the sides are equal. It's an equilateral triangle. Okay, or a regular triangle, one can say, but we haven't used that word yet. Is this one isosceles?
Could be. No, can't be.
So it is, but we'll get there. Yep, it is. Any other types of triangles? We'll get there. It is. I guarantee it is. Any others? This pretty much runs the gamut, right? Like this is most of them. Now, there's of course some other things that we could do, but when we're looking at these, we're going to focus on two of these specifically today. So in our section today, we're only going to knock out two of those, but in 4.2, we're really just worried about the side lengths of specific triangles. And we get two different types of triangles that we'll deal with. So to start this off, the first specific type of triangle that I'm after and that we're going to talk about is we're going to sneak in a definition. We are going to go ahead and talk about our isosceles triangles. Now, I'm just going to use triangle, the shape of a triangle there, to be triangles. Hopefully that's not like too crazy here. But here we are. When we write our triangles, isosceles is one very common type. When we define this, we're just going to simply, it's really easy to define, a triangle, and I'm just going to keep using this unless there's objections for a triangle, with at least two congruent side lengths. I'm going to say two congruent sides. Okay. Now, the at least part is what's super duper important here. Because a moment ago, I had an equilateral triangle on the board. that had 3 side lengths the same. And just check my math here, is having 3 of something, at least 2 of them. So it does classify here, just by the definition of what we say this is. Now, beyond there is some pretty handy stuff that winds up happening. Immediately in this chapter, we're going to get a bunch of theorems. Just so you're aware, whether we prove all of them or not, we will decide. So we jump in immediately with a theorem, and we're going to call this theorem 4.1, and we'll call this the isosceles, and I'll show you my shorthand. When I write isosceles just in my notes, this is where I stop. I just call it isos with a SC, so it's clear that what it's going to end with. This right here is my shorthand for isosceles. I'm going to actually write it out. Isosceles triangle theorem. Now, we will get back into proofs eventually, and we'll see when we fully get there, but we're going to get our picture first and see if we can't make sense of what the theorem says. If we have to put it into words, absolutely we will, but I think that your intuition here might be okay. So I'm going to sketch in, as best I can, an isosceles triangle. Now, do we ever just blindly trust the picture? No. Right now, if I want this triangle to be isosceles, it's believable that it could be, but until I put some marks on here, and I'm just going to call this ABC, until I put some specific marks on here, I'm not convinced that it's isosceles. What has to be true for it to be isosceles? At least 2 congruent sides. Doesn't matter which sides, right? I'm going to go ahead and say it's AC and CB. Okay, that's the sides that I'm saying. We have now 100% certain an isosceles triangle. Now, this theorem tells me a couple things, and I'm going to add pink stuff. It is entirely optional if you want to add it. Is there anything else on this triangle that has to be the same? If these sides are the same, do I get anything else for free, do you think? There's a pair of angles that I guarantee are also congruent. Does your gut have an intuition as to which angles? And in intuition, A and B. Anybody else think that A and B should be the same? Like, it seems reasonable, right? Okay, I'll go back to the red color. We're going to just write this out, and we're going to put them both here. Now, we're going to sneak in a definition here. If I said, where in the triangle is this? And we're just going to throw this out the first time. This is a cross. This angle A is across from which side? CB. Do we all agree that this angle is across from this? Okay, now, if you struggle to see that, because it's weird to talk about across, somebody might think, oh, it's this, because it looks like it's on the other side, and I get that. But if it's next to it, the words that we use is adjacent. So this and this are adjacent, these two, to angle A. This is the opposite side, or across the triangle. So when we see these, we're going to define these two angles as follows. We're going to sneak a definition here. We get base angles. Now, it always sounds weird because naturally, if I talk about the base of something, your mind, because we live in 3 dimensions and we do this all the time, you think of the same part. This cup right now, you guys can see it. If I said, what shape is the base of this cup? What would you say? So the cup is a cylinder. What about just the base of it? Because you guys are all thinking about this part, right? If I laid it down on its side, which I can't do because it's full of stuff, would you change what you call the base? Or would you just recognize that it's just tipped over sideways and it still has a circular base? I don't have an empty cup. So this base is also a circle, right? And if I set it down, the base is a circle. Okay, everybody see this still? Could I still say the base is the circle still, though? Because we all understand that normally this isn't how it sits. Like, we use base to represent the bottom of something pretty commonly, but it's just because we're so used to setting stuff down on surfaces. Okay, when we look at this, if we talk about the base angles, it does indicate that there is one side of this triangle that we would call the base. The way that it's sitting, what would you guys say is the side that's the base of this triangle? AB is the side that's sitting on the ground, quote unquote, right? Now, if I just did this, and you don't have to draw this one, but let's say I did this triangle instead. And this is going to be weird for me to do. And I said, if it's the same triangle, I'm trying not to draw the exact same triangle. Let's say that this is A, B, and C. So we get the exact same marks. What side is the base of this triangle? Does your gut say? So BC is the natural choice, but if, you're right, I agree with you. Based on the discussion about the cup and that stuff, AB is what we'd still call the base, even though it's tipped over sideways. Okay, we are going to make that the norm. When we talk about our base angles, these things are going to be the angles, and I'm going to say opposite, but you could use the word across instead. Not opposite, but opposite. The angles opposite from congruent sides. Okay, which means very specifically in this triangle that I have on the board, what are the base angles?
Angle A and angle B.
These are my two base angles. Now, in an equilateral, it winds up not mattering because if they're all three the same length, it doesn't really matter what side you put as the base because they're all the same. Okay, here is our isosceles theorem, and I'm going to use if and only if, which means what? What's the difference between if A then B and A if and only if B? So the equal is a good thought. Does the direction matter? It's both ways. If A then B and if B then A. Like it goes both directions. So here we go. If triangle ABC, nope, I lied. I'm going to automatically get rid of the if because I just talked about this. We're going to say triangle ABC, sorry about that, is isosceles if and only if the base angles are congruent. You can write if and only if as 3 words if you want. You can use IFF, or you could use the double implication. What this means is that and we'll actually just make sense of this. If you give me an isosceles triangle, then it tells me 2 big pieces. I have a pair of base angles that are congruent, and opposite from those are the sides that are congruent. Okay, do we need to define the word base as well? Like we have base angles. Can we just say base and just write it here and not write the definition of it? How do you find the base of an isosceles? Say that again. So the opposite of a side would be an angle. So we won't have to write it. It's clunky, right, to try to word it. 2 ways that I would explain this. The base of a triangle is between the base angles, which seems silly, but for sure that's a way to say it. Or it's the side that is opposite from the non-congruent angle. Like either one of those would take us here. Now, as we look at this, we can immediately start to see kind of just how this works. So let's do an example. I'm going to keep this up as long as I can. And here we go. I want us to find length. And it'll be clear what we have here in just a moment. We're going to use this theorem, and we're going to find some lengths. So for our first one, let's check it out. Let's suppose that we get the following lovely triangle. And I want to reemphasize, am I ever going to spend a ton of time drawing these things perfectly to scale? No. Now, occasionally I'll try. I'm never going to intentionally trick you. If it looks like a right angle, it's not until it's marked. I will try to make it always look like it. But let's get some measurements on here. So I'm going to put an arc, and I'm going to name this triangle, I suppose. Let's call it Jeff. J-E-F. Okay, here's all that I know. I'm told that angle J is congruent to angle F. So I'm just going to put an arc across each of them. Okay, beyond this, I'm just going to add some lengths, but I'm just going to draw them on the picture. So we're told on this figure that EF is 4x plus 5 units. Now, first thing, how do I know that as I look at this, that's not a degree? Dang it. How do I know that's not an angle? There's no degree on it. All right, cool. Thanks for playing along. All right. Let's say that side JE is 8x minus 1. Again, no degree symbol. And finally, side JF is 2x plus 11. Okay, and I lied. I was going to try to keep the theorem, but I assume you guys can see it in your text or on your notes. Okay, what am I trying to find here? The lengths. So when I say the lengths, and I don't specify, what's one of the lengths that I'm after? JF, good. JF is 1. And we're going to use JF equals because we're going to find an actual length. I'm just putting where my answers are going to be in the end. We'll do all of our scratch work here. Give me another side. If I went JF, the next, and I'm just going to shove this one in there. Is there a next natural choice to write? We went from J to F. FE is what I'm going to write. I don't really care about your order here, but I'm always going to be consistent. JF, FE, and what's the last one if we keep that order going? EJ. Awesome. Okay, I'm only doing this because we're going to put our answers here, which means everything over here can just be the work that goes into it. All right, right off the bat, what sort of triangle are we working with? So we'll help with it. Isosceles. Isosceles. Why do you think that triangle JEF, Andrew, is isosceles? Now, this is just like the thought that's going into it. You don't physically need to have this, but it's a good representation. Because, and I'm going to use these 3 dots right here to represent because. Pretty common. You can use BC. Why is this isosceles? Angle J is congruent to which angle? F. Did the lights just flicker or did I blink and not notice it? Okay, cool. All right, the second we have this realization, and we're not doing a proof right now, but it's going to feel kind of like it. The second that I say that this is isosceles, is there any other mark that I can put on this? Good. So I know I was going to say for sure and for certain, and it was going to come out as for certain, that JE, that segment, or the side of my triangle here, is congruent to what? Good. I'm going to call it FE, and I don't like. You're cool to call it EF. It's just when I'm working up away from like. Doesn't matter how we pick that. Doesn't have to match. Okay. The second I put those on there, does it give me everything that I need? You don't think so? How on earth could we find the side lengths? Now, to get the side length, there's some little bit of algebra hiding in here. What do I need? I need to find the value of something. Let's find the value of x. Is that what congruent means? If they're congruent, are their lengths equal? So little tiny bit of algebra, and here is where on our next problem, maybe I can throw in a little bit of factoring stuff. I know that 8x minus 1 must be equal to what other value? 4x. Perfect. I'm going to give you guys like 30 seconds to do a little bit of algebra. Bruh. Thought you were raising your hand. No. Got me good. Cool. Solve this for x for me. I'm going to give you a little head start. What is the color? Red. Okay, and I'm going to simplify my fraction. But did you guys get the same thing? You might have stopped at 6 over 4, 3 over 2, or 1.5. I don't care which one it is. We have the value, right? Are we done? No, and the convenient part is I know that because here's where we're going to write our answers and we haven't filled them in yet. The fact that x is 3 halves. I typically don't, but do I care if you change this to 1.5 because you're using a calculator? I'm cool with it. You can. You're good. Like, totally fine with it. 1.5 is easier to think about, probably for everybody. Let's find one. Let's do JF first, out of no particular reason. What's 2 times 1.5? Plus 11. So I'm just going to have that. I'm just going to write 14 here. And all we're doing is plugging in x into that value. It's 14. I don't know what the units are, so I'm just going to call them units. No idea what it is. What's this one? What's 8 times 1.5? 12 minus 1. 11. And that was JE or EJ. Do I have to work out anything for the last piece? I did EJ, I'm pretty sure. It's 11. Did you have to work that out or did you just know that? How do we just know that? Because you're right. They're congruent. They had to have been the same, right? There's no other option. If we wanted to check, and it's always a good practice, we could probably do this. This is 1.5 times 4 or 1.5 times 4, which is 6 plus 5. It is 11. We're done. Piece of cake. Okay. We are going to do one more, and man, we could probably do a proof here. Yep. We'll see if we get a proof or not. One more big idea, though. Should we do one more like this? What if we added some like factoring and stuff into it? Cool. All right, so let's do B, and you may have to look at your notes from the stuff that we did yesterday. I'm only going to give you 2 sides of a triangle, I think. So let's say here's this triangle, and on this triangle, I'm going to say that this is 12, and this is 12. Not even going to bother to name the triangle. And let's say that I have x squared plus 2 degrees down here. And I get, that's going to be a weird one. Is it okay if the numbers don't make perfect sense with real world? Okay. Negative, I got to think it out. Negative 3x degrees. Now, I doubt that this is going to work out realistically, just so you guys know. But it's just setting up the problem that I care about way more. Okay. All I want us to do for this problem is to find x, and specifically the value of x, I suppose. Now, that is negative 3x. And it means our triangle might not really exist in the end, but we're just going to let that ride for now. Like, we're just setting up the problem. How on earth, Andrew, could I possibly find x?
You set it up with x squared plus 2. Like you set them up next to each other.
When you say set them up next to each other, I'm okay with the x squared plus 2. And if I set them next to each other, it's like this. What am I missing?
Plus sign.
Why plus?
Because it's carried over from the x plus 2.
So I'd be careful. Like you're trying to mix this idea up with other stuff that we've done, which is natural. Real quickly, what kind of triangle is this? Why do you think that?
Because 2 with the same angles.
So I never said these angles were the same. But these are definitely the same. We have 2 sides of a triangle that are congruent. I haven't put the marks, but I gave you the lengths. The fact that those are 2 congruent sides means for sure it's a what? And if the sides are congruent in an isosceles like this, it means that which angles are also congruent? Good, love it. The base angles. It means I also get, I'm going to change color while I add these. These got added just to make it nicer. And I guarantee that these are also congruent because they're the base angles, which means instead of plus, Andrew, what should I put in between these?
Equal.
Love it. you now get to solve this for x, and we're going to see if any of the answers really make sense. That's fair. They're both positive. Isn't it 2 and 1? We should have made that positive 3x in hindsight. But that's okay. All right, help me solve this. And we didn't do the real solving stuff, so we're taking a little bit step past where we went with algebra the other day. If I want to be able to use that wonderful F word, I want it on one side. What should I move over to the other side? How do I move this over to the other side? Okay, I'm going to add 3x to both sides, and I'm going to sneak it in right in the middle since there's no like term. Now, very similar to what we were doing with the algebra stuff, there's one step forward, but I'll help you with it. That leads us to x squared plus 3x plus 2 is now equal to what? 0. Now, the equal 0 part, that's the only thing that we didn't talk about the other day in our algebra review. How do I factor this? You might have to check your stuff. Anybody but Lily, not because I don't want to hear what you have to say. How do we factor this? If you have to look back at the last couple of days of notes, that's cool, but I'm stuck. What's the leading? Shortcut. Oh, we can do the shortcut because the leading coefficient here is a what number? A 1. Now, you never have to write it. I'm going to make it obnoxious and stand out, though. That's a 1, which means there's a shortcut. Now all we need is, how on earth does that shortcut work?
What? 2 times 1. What do the things equal to 3?
Okay, so I heard 2 things. I like what you said. I like what you said. We should check for GCF, but there's nothing that goes into all 3 of them. But always that should be a thought. Now, Carson's suggestion, even if we ignored GCF, was to multiply this and this. We get 2. I need numbers that multiply to be 2, but add up to what? 3. Anybody come up with those? 1 and 2, which means if we use a shortcut, and we don't typically write this, but do you guys agree that was a positive 1 and a positive 2? Okay, that little change there might make this a little bit more clear. How do I use the shortcut then? X plus 1,
X plus 2,
and x plus 2. And Lily, I do think these make sense. And we'll see here in a second, because I know that I've completely 180'd, which is a little algebra or geometry play on words for you. Okay, we did everything like this the last couple days without the equal 0 part, right? But I have a riddle for you, and it's really not a riddle. I'm thinking of a number. I'm not going to tell you what it is. But I know that if I multiply it by 5, I get 0. It has to be 0, right? Like there's only option. I'm claiming that this number times whatever this is in the parentheses for some x value, this times this is 0, right? Which means one of them had better be a 0. If we set this equal to 0, which most of you and everybody I think can probably do this in your head, but if I take this factor and I set it equal to 0, what do I get for x? -1. And if I take this factor, x plus 2, and set it equal to 0, what do I get for x? Okay, now we look at this and you may be tempted to say, this doesn't make any sense because we get negatives, right? I think it does still make sense. Like the negative is weird, but let's just see what happens here. If I plug in, and I'm just going to check these. These are my 2 possible answers right now. If I plug in a -1 for x right here, what is -1 squared? Plus 2. That would say that this is 3 degrees, which it's not to scale. It'd be like way smaller, but it could happen. If we had to plug in -1 here, what's -3 times -1? Are they both the same and they would match? So x would be 3 degrees. It's way out of scale, but my answer makes sense. This one works okay. Let's check this one. Let's just try -2 as well. If I plug in -2 and I square it, it gives me plus 2 is 6 degrees. And if I check it on the other side, -3 times -2 is, did we both get the same angles again? And they're positive angles now. I don't care about x, but positive angles make sense. 3 and 6 degrees is reasonable for a triangle. It's super tiny, right? It's like nothing. But that triangle could exist. It's just not drawn to scale. For this, what answers work then? I say values in this one. What's our total answer? X equals? Or -2. Now, I have good news and bad news. The good news is that this is way harder than any of the problems that you're going to get to see because normally people don't hit factoring super hard in geometry. I'll tell you, I'm going to continue hitting it super hard in geometry because we spent like 3 weeks in Algebra 2 just now relearning factoring. And it's very clear that people didn't factor a whole lot in geometry last year. So we're going to make sure that we have it. Okay. We will pick up here tomorrow. You guys have a wonderful day. No homework. Go to the games. Cheer it up. Pink tonight, right? Yeah. There's pink wigs, pink mustaches, pink beads, pink tutus, pink boas. There's so much pink, it'll make you think. I don't know. I'm not. Me and Kendrick stopped hanging out. All right. Peace out, Raiders.